In this video, I'm going to put together what you've learned in the last 4 sections to draw a curve of a polynomial function. So calculus can provide us with very useful information for drawing curves. So you've learned that the first derivative, y prime, can tell us where a curve is increasing and decreasing. And then the second derivative, y double prime, can tell us where a curve is concave up and concave down. So I like to follow these 9 steps, which I put together for you here, to kind of go through the kind of a little checklist when you're drawing the graph. So the first thing you should look for when you look at the function is to find the domain. After you found the domain, find the x-intercepts, which you can solve for by setting y equals 0 and solving for x. And then, of course, find the y-intercepts. So now you're going to plug x equals 0 and solve for y. Now you might not have any intercepts, and then if it is too difficult to find, you might want to use a calculator to kind of look it up. But that's kind of weird because we're trying to do this graphing without the calculator. All right, now you're going to use the original function to find any symmetry. Now we haven't talked about this for a long time, so let's review what this is. So we say that f is even if, when I plug in negative x, I get the same value, or expression in this case, if I plug in f of x. So an even function would look something maybe like this. And the reason that it's even is because the distance, negative x, is equal to the distance x, and it's actually the same value of y here. So these are the same. We say that f is odd if, when I plug in negative x into the function, I get negative f of x. So let's say that I have, and try to draw something like this. Okay. Okay, so this time I'm saying that this distance is equal to this distance here. So when I plug in negative x, and I plug in x, I get the negative of what the y value was down here. So this would have been, let's say, negative y, and now this is going to be positive y. We often say that this one can be reflected, or sorry, when something is even, we often say that it can be reflected over the y-axis. And when something is odd, we can rotate it 180 degrees, and it still looks the same. All right, so number 4. By computing the appropriate limits, we're going to determine whether the graph has any vertical or horizontal asymptotes. So remember, we check for horizontal asymptotes by computing the limit of the function, excuse me, as x approaches positive and negative infinity. We locate any vertical asymptotes. So we're going to look at isolated points or endpoints, which are not in the domain. Sorry, that's what a vertical asymptote is. And we can check this by looking actually in the denominator of a rational function. So if x equals c is such a point, we can compute the limit of f of x as x approaches c from the right or from the left, and it will give us the vertical asymptote. Now, like I said, this is only done when it's a rational function because polynomials won't have any asymptotes. Or vertical asymptotes. Actually, it won't have any asymptotes. So next we're going to find our first derivative, y prime, and we're going to then use a sign chart to figure out where the graph increases or decreases. And then we're going to use the y prime sign chart then to locate any relative max or relative min. Or you can call them local max or local min. We're going to then find the second derivative, and we're going to use our sign chart to find concavity. And then if the concavity changes at that point, these are inflection points. So again, you're using your second derivative to find these inflection points. And then put everything together from these 8 steps to draw your graph. Now you might be thinking, well, why do we even have to do this? Why don't we just use a graphing calculator or a computer to draw the function for us? Now, that's great and all, but the calculator and computer can't often tell us what features might be really interesting, or you don't know where to zoom in because you wouldn't have known what the graph looks like except to plug it into the calculator. So by using calculus, we can actually find some special features that maybe you didn't know about. All right, so let's do an example. So the example we're going to do is x to the power 5 plus 5x to the power 4. All right, now since it's a polynomial, we know that the domain is all real numbers. Intercepts, when we plug x equals 0, we get y equals 0. If we plug y equals 0, then we have 0 is equal to x to the 5 plus 5x to the 4. So we need to solve this by factoring. So I'll factor out x to the 4, and I have x to the 5 left. So here I see that x equals 0 and negative 5. I like to put a box around everything that I know. So I know that y equals 0, or actually even better, let me put this in a different color. I have a point 0, 0. I also have a point y, so 0, 0 again, but also negative 5, 0. Okay. Any symmetry. So what we're going to do is we're going to calculate what negative x, f of negative x is. So when I plug it into my original question, I get negative x to the power 5 plus 5 times negative x to the power 4. So this gives me negative x to the power 5 plus 5x to the power 4. So when I raise something to the power 4, that's negative, it's going to become positive. So that's why I've left the negative sign out. All right, so I can check, and I can see that this function here, the negative x to the power 5 plus 5x to the 4, is not the same as the original. Okay, what about if I put in negative f of x? We get negative x to the power 5 plus 5x to the 4, which gives us negative x to the power 5 minus 5x to the 4. So now we check to see if these two are equal, and they are not. So there is no symmetry here. So therefore, no symmetry. All right, asymptotes. There are no asymptotes because this is a polynomial function. So no asymptotes because polynomial. So let's go on to our second derivative. Our first derivative. All right, so y prime is equal to 5x to the power 4 plus 20x cubed. Set this equal to 0. And let's do our factoring at the same time. So I'm going to factor out a 5x cubed. So I get x plus 4 left inside, and x is 0 and negative 4. So I'm going to do my testing. And we put this into f prime. So I'm going to test a number, so negative 5, let's say, and I plug it into here. That's going to be negative. This will be negative, so this is going to be positive. So it's increasing, plugging a number between negative 4 and 0. I like to plug it into here where it's factored already. So then we get a positive and a negative. So this is negative, decreasing. And then I plug in a number greater than the 0, and that's going to be positive. All right, so I have a relative or a local max at x equals negative 4, and I have a local min at x equals 0. So to calculate what that exact point is, I'm going to plug negative 4. Now, because I want to know what the exact point is, I'm going to put it back into my original question up here. So when I plug negative 4 back into the top, I get positive 256. So I'm going to say that this is going to be 256. I'm going to say negative 4 and 256 is going to be my maximum point. And then my minimum point when I plug in 0 is going to be 0, 0. Okay, so I'm going to put a box around this because I wrote it in a different color. So I have these points here. Notice these are actually the same. Let's now find my second derivative. So I have y double prime equals 20x cubed plus 60x squared. Set this equal to 0. Factor out a 20x squared. So I have x plus 3. So here x equals 0 and negative 3. So again, let's do my sign chart. This time, remember, we're doing concavity, so I'm going to use my second derivative. Plug in the numbers, less than negative 3, between negative 3 and 0, and greater than 0. And I actually get negative, positive, and positive. So to help me visualize, this is going to be down, up, and up. So therefore, because at negative 3 we change concavity, I'm going to have an inflection point at negative 3. So I'm going to plug that in to find out what that is. So y, so actually let's say that we're going to go f of negative 3. So negative 3 to the 5th plus 5, negative 3 to the 4th. That gives us 162. So I have my last piece of information, negative 3 and 162. Okay, so I'm going to put all of these points together to help me draw a graph. Okay, so I'm going to squeeze that down here on the bottom. And I have 0, 0, negative 5, 0, so I need to put some markings. So negative 1, 2, 3, 4, 5, 6. So I don't really need to worry about that side. So I have negative 5 here. Okay, and because I know I need to go all the way up to 162 and here even 256, I'm going to use a scale of 100. Now this won't be perfect, but it's a rough sketch, but a good rough sketch. All right, so I have my scale here. All right, so let's plot our points that we know. We have 0, 0, and we have negative 5, 0, which are our intercepts. We have a maximum at negative 4 and then 256. And we have our minimum at 0, or a local minimum, so we know that's our lowest point. And then we also have an inflection point at negative 3 and 162, which I will say it was about here. Okay, so we know that up to negative 4 it increases, and then from negative 4 to 0 it decreases, and then after 0 it increases back. Now I don't want to just draw straight lines here to draw the zigzag, so we're going to use this concavity to help us. So when x is less than negative 3, we know that this is concave down. So think of it as it's going to spill water. So we have from negative 3 down, this will be cut up upside down. Then from negative 3 to 0, it's all concave up. So that means that I have to curve down. Well, sorry, I'm going to exaggerate that a little bit too much. So we're going to curve down, hit 0, and then curve back up. And then there we have it. So please make sure that you use your concavity and your inflection point to kind of help you draw and outline the graph at the very end.